Good afternoon and welcome to today's webinar titled Watershed Modeling Using HSPF. This webinar is sponsored by EPA's Water Quality Modeling Workgroup. I am Dino Marshallonis with US EPA and I will be moderating today's webinar. Thank you all for joining us today. First, I'm going to briefly summarize some of the features of today's webinar. We hope you will have lots of questions, and if you do have a question, please type it in the questions box on your control panel and click Send. If your control panel is not showing, simply click on the small orange box with the white arrow to expand it. If you have any problems viewing the broadcast, just let us know in the questions box and we will post an answer in that same box. A phone number is also available on your control panel if you are having trouble hearing audio through your computer speakers. This webinar will be archived for later viewing on EPA's Water Quality Modeling Workgroup page, and we will provide that archive link for you on a slide at the end of the webinar. Also at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. The materials in this webinar have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of US EPA. Mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. The purpose of the webinar series is to help water quality professionals better understand water quality modeling and how models can be used to solve the problems facing water quality regulators. The target audience for the series is a water quality professional who may use, want to use, or review models as part of their job, but who do not necessarily have a modeling background. As such, we are assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. Today's webinar is the 9th in our water quality modeling series. All of the past webinars have been recorded, archived, and posted to EPA's YouTube channel website. Links to the archived files are available on our Modeling Workgroup website. This URL will be shown at the end of today's webinar. Further, in a few weeks, a copy of today's webinar archive will be posted on the same website. We encourage you to listen to any of the previous webinars or share access to these files with your coworkers. Today's webinar builds upon the information presented in the earlier webinars, and your feedback on the series and content has helped to shape each installment of the series. At the end of today's webinar, there will be a survey where you can provide feedback and additional comments. We encourage you to let us know how we're doing and what you like and what you don't like. And with that, I am pleased to introduce today's speaker, Tony Danigian. Tony is currently a principal consultant at Respect Consulting and Services and was formerly president and principal engineer at Aquaterra Consultants. Tony has more than 4 decades of experience in the development, testing, and application of computer models for assessment of environmental contamination and water resources planning problems. He is an internationally recognized authority on modeling nonpoint source pollution and chemical migration in the environment, primarily for water, soil, and groundwater systems. His recent research and application studies have focused on regional and watershed scale modeling of nutrients and impacts of management practices, model validation issues and procedures, and the evaluation of control alternatives, such as best management practices, including LID, conservation tillage, and remedial actions at waste sites. Furthermore, Tony was the principal developer of the early runoff models, EPA ARM and NPS, and was senior advisor to the development of the HSPF model and subsequently basins. He continues to participate in both model applications and code enhancements for both HSPF and basins, and he has been a primary lecturer for basins and HSPF training workshops sponsored by the US EPA, US Geological Survey, and others during the past 30 years. Before I hand today's presentation over to Tony, we'd like to ask you, our audience, to participate in a few short poll questions. In a moment, you will see a slide with a blue background, a poll question, and some radio buttons. Please select the radio button or buttons to respond with the most appropriate answer. We'd like to gather your responses to these 3 short questions now, and then at the end of today's webinar, we'll ask a final question. So you should be able to see the first question on your screen, and if you could select one of the radio buttons. And unfortunately, you don't see the results, but I do, and I will just say that it looks pretty across the board, evenly spread between never heard of it, used by my organization, beginners, very few expert users on this call. But mostly, we're looking at beginning users and used by my organization. So let's move on to the second question. You should see that on your screen now. Please take a moment to select all appropriate answer choices. Okay, a lot of people are using HSPF for TMDLs, stormwater, and urban ag BMPs. About 75% of people are using HSPF for TMDLs. About 50% for stormwater and 50% for urban agriculture, with about 30% for NPD as permitting, about 25% for flooding issues and mitigation. So maybe let's move on to the third question. You could respond to any of the radio buttons that apply. We'll take a brief second to allow you all to enter your answer. All right, it's pretty evenly dispersed, about 40 to 45% across the board. A lot of people are using other models. About 60% of you have selected F for others. The next highest rank is basins at 45%. All right, well, thank you all for answering those questions and participating. I'd like to make one final announcement before we kick off the presentation by Tony. We will try to answer as many questions as possible throughout the webinar, and we'll be asking questions for our speaker at various points throughout his presentation. Please remember to type your questions in as the webinar progresses, and we will try to answer as many of those questions as possible. And with that, I'd like to hand the floor over to Tony to kick off today's webinar.
Okay, thank you for attending, everyone. And I appreciate you taking time out of your busy schedule to learn a little bit about HSPF, its capabilities, describe the application procedures, including key aspects of the application involving calibration and validation, and then select provide results from selected case studies showing the types of information you can get from HSPF and the types of things you can use it for. HSPF stands for Hydrologic Simulation Program FORTRAN. It's a continuous simulation model, and I'll discuss what I mean by continuous simulation in a few subsequent slides. You can use it for both developed and natural watersheds and water systems. It includes both land surface and subsurface hydrology and water quality processes, along with complete simulation of stream and lake hydraulics and in-stream water quality processes in order to basically simulate what's happening on a watershed. The other capabilities in terms of data management, time series statistical analysis, and the fact that it's the core program, watershed program in the EPA basin system, and the Army Corps of Engineers watershed modeling, water modeling system. It's has been developed and maintained by the U.S. EPA and the U.S. Geological Survey since its release in 1985, and we're up to release 12.4 will be coming out in the next few months. I'd like to point out it's often difficult to get federal agencies to agree on too many things, but in this case, both the EPA and the Corps of Engineers have agreed that HSPF provides the the type of capabilities that are useful for watershed analyses. Continuous simulation means that we're representing the hydrologic processes, storages, and fluxes for a watershed continuously for many days to multiple years, and usually on a time step of usually less than 1 day, but sometimes on a daily basis, and in the range of minutes to hours. So we represent what's shown here in this diagram of the hydrologic cycle in terms of putting in precipitation and evapotranspiration to the model, and the model takes those inputs, those forcing functions, and represents runoff, interception, evaporation, subsurface flow, and stream flow. It represents the other portions of the hydrologic cycle. And the types of information you can get out of a continuous model include storm hydrographs at the bottom here, detailed simulation of storm events on the watershed at an hourly time step or less, depending on the time step of the input data. Those can be aggregated to daily flows, and that's what you see here, a trace of daily flows for a 9-year period, 6-year period from 2000 to 2006. You'll see the flows in the range here on horizontal, on the vertical axis, time period, and then above that we usually put the driving function, the precipitation. So you can see how the watershed responds to the input precipitation. And if you analyze these flows on a statistical basis, you can generate what's called a flow duration curve, where you see the flows again on the vertical axis, and this is the log scale showing the large variability in flows, and on the horizontal axis, it's the percent chance that the value has been exceeded. So the very high flows are exceeded very infrequently on a fraction of the time step, whereas the base flows are shown here being exceeded on the order of 99% or so. The flow duration curve is a key aspect of assessing how the model behaves over the full range of flows, how well it represents your watershed, both high flows, low flows, and moderate flows. And this key aspect in performing calibration is looking at the flow duration curve. The components of water quality are then the problems and pollution sources are imposed on the hydrologic cycle, and the hydrologic cycle drives it, but man's influence also affects it. So we see all these types of activities that occur in the watershed, tillage, agricultural activities, discharges from treatment plants, industrial discharges, human activities in urban areas, all contribute to potential contaminants that can move over the land surface and through the soil to the stream channel, and then down through the stream channel, including stream interactions and transformations. To try to model this complex system, you have to represent or have a model that represents the various processes shown here. So we need to have, from the land surface, we need to know what's coming into the stream channel. So the model needs to represent what's coming off the land in terms of runoff quantity and quality, sediment erosion and solids, overall quality such as water temperature, dissolved oxygen, BOD, all of those kinds of constituents that are contained in runoff quality, along with sources from the atmosphere and any other inputs needed by the in-stream channel simulation, such as water temperature and dissolved oxygen. Then the in-stream portions take over and provide the hydraulic, sediment transport, sediment, contaminant interactions, the biochemical processes that involve nutrients and algae within the stream channel. It needs to accommodate point sources, allow for lake and reservoir simulations, and then include the impacts of bottom processes, benthal processes on the overlying water quality within the stream channel. So these are the components of water quality models that need to be included for simulation of a complex watershed system. Now, HSPF attempts to represent these through a variety of application modules. We have the 4 modules shown here include per land, impland, retreads, and BMP. FORTRAN refers to any pervious land surface in the watershed. So any surface that can infiltrate water is represented by FORTRAN, and these are the types of constituents, or the different subroutines within FORTRAN within the model code to represent snow, water movement, the hydrologic module within HSPF, and water movement through the soil, over the land surface, and to the stream channel. Sediment erosion, general water quality, it can includes algorithms for pesticides, nitrogen and phosphorus, and tracer elements in order to help calibrate water movement. The impervious surfaces are represented by impland. Again, snow, water, solids, and quality. It doesn't need to represent soil processes. And within the stream channel, the module retreads is used to represent both free-flowing streams and completely mixed reservoirs. It includes hydraulics, conservatives, water temperature, sediment, any kind of non-conservative reactive constituents, the BOD-DO cycle, and then nutrients and algae and plankton. So it includes a full suite of water quality capabilities just short of fish species. So it includes algal simulations. And then the BMP module allows you to represent the effects of a variety of best management practices, detention basins, buffer strips, and so forth in terms of removal constituents, removal efficiencies. And this is so you can represent ways to mitigate the impacts of human activities on the watershed and improve reduce loadings to the stream channel. I'll go through each of those structure charts just briefly. This is a structure chart showing the various subroutines within the FORTRAN module. And again, the goal of FORTRAN is to simulate a pervious land segment or a piece of land within the watershed that is pervious. We have a variety of routines in here to include or accept air temperature and make any necessary corrections due to elevation changes and differences. The snow module is shown here, and P-water is basically simulates the water budget and provides the transport mechanisms for the other constituents. Next, we have a sediment module that simulates sediment erosion. PS temp simulates soil temperatures, PWT gas, water temperature and gas concentrations, DO and CO2. And then PQual is the general module for simplified representation of qualities constituents, allowing it to accumulate and build up and then wash off the land surface. And PQual is that routine that represents those processes. We also have a detailed, what we call an ag chem module that does detailed soil processes of nutrients and pesticides. It simulates, actually allows for accepting pesticide and nutrient applications to the land surface and to the soil, and then simulates a wide range of processes that include the nutrient cycles within the soil, pesticide sorption, desorption, and decay, and then all the nutrients and a tracer constituent to allow, in many cases, to calibrate some of the data we see available from field studies. The implant chart is similar but simpler because we don't need to represent the soil processes as much as the surface. Again, the air temperature and snow modules are used. High water simulates the water budget for the impervious land segments. Solids does accumulation and removal of solids. And then these two simulate water temperature and dissolve on impervious surfaces, and then the water quality constituents that wash off from impervious surfaces such as parking lots, streets, roads, roof surfaces, and so forth. It's analogous to the PQual module in FORTRAN. IQual represents the impervious contributions. And then we have the retreads structure chart to simulate a mixed reservoir, simulates the hydraulics, advection by head count, conservative constituents and cons. Heat reach does a heat balance, calculations for the stream channel to simulate water temperature. FORTRAN simulates inorganic sediment in terms of detailed particle sizes, sand, silt, and clay, scour and deposition within the stream channel. Stream channel is represented by FORTRAN. GQual is used to represent any kind of generalized user-specified water quality constituent, and typically these are when the user specifies particular metals or bacteria or fecal coliforms. That's represented by within GQual. It also allows you to represent the interactions between your constituents and sediment in terms of partitioning both in the water column and within the bed. So it allows for complicated sediment-contaminant interactions. And then HydroLogical simulates constituents involved in biochemical transformations. All the nutrient constituents are represented here, nitrogen, phosphorus, and carbon, and even the nitrogen components, nitrate, ammonia, organic, and phosphate and organic P, along with the biological simulations in terms of algae and phytoplankton in the stream, in the water column, and then benthic algae within the stream channel, bed. To represent a complex watershed, we go through a process called segmentation, where you divide up the watershed into pieces that we can then convey information to the model that this portion of the watershed has different characteristics, different inputs than another portion of the watershed. So you simulate it differently. You simulate same processes but with different inputs and characteristics. So we have a watershed here. We would typically divide it up into multiple areas depending on how many the inputs in terms of precipitation, temperature, the forcing meteorologic inputs. We look at the physical soil characteristics and channel properties and land use. And then in deciding where we want outputs to use for decision making, that also will impact to the extent that you divide the watershed up. It's basically the spatial and temporal resolution of the model and adapt that for what you need for your particular problem you're analyzing. So in this particular example, we had 3 different meteorologic zones, an upper, middle, and lower, and then we have a series of stream reaches. In the upper areas, we have our ProLand module would simulate a variety of constituents and water in this area with these inputs, put those into the stream channel, route those downstream. They would receive inputs from calculations performed in segment 2 here and route those down. And then finally in segment 3, those would provide contributions to the stream channels and route it through to the outlet. And so this process of segmentation I'll go through, and I'll show you some examples of that as we go through the webinar. There's also a vertical segmentation in terms of the soil profile. It's used primarily by the AgChem model, but it looks at a shallow surface layer on the order of a centimeter or of a quarter of an inch or so. An upper zone soil layer where inflow is assumed to occur, and typically this is on the order of about 6 inches. The lower zone represents the depth down to the bottom of the crop root zone, and then the shallow groundwater that contributes back to the stream channel. So all these soil layers are represented in the model when the AgChem module is being used, and we're maintaining storages in each of these soil layers to perform the simulation. So some of the strengths of HSPF include its comprehensive representation of watershed land and stream processes, its allowance for a wide range of pollutant sources, including all non-point sources by multiple land uses, point sources, atmospheric deposition, contributions from the stream channel or the stream bed itself. It is highly flexible and adaptable to a wide range of watershed conditions. It's been applied all over the world in deserts of Saudi Arabia, although even deserts have rainfall occasionally. It's been used in dry areas, semi-arid areas, especially out here in California. But it's also been used in Korea and Japan and in Europe. So it's had wide application and is widely adaptable and flexible in its application. It has a well-designed code in terms of modularity and structure. It used to be on the order of about 1,000 subroutines. It's probably gone up from there, but it runs very efficiently and very quickly in most normal setups. It includes some companion databases and supporting programs. It's currently housed within the basin system, and I believe Dino had mentioned that a basins webinar is planned sometime in the future that will give you more information on that. And it has a graphical user interface referred to as Win or Windows HSPF. Its ongoing development and support has been by the US EPA and USGS, Geological Survey, and I'll mention a number of groups that have supported code enhancement. And the code has gone through strict QA control through a joint agreement between the US EPA and the Geological Survey. Now, it does have limitations, and it's as important to know its limitations and weaknesses as it is to know what it can do. So it does require an extensive amount of data, and Basins has been a big assist in this area in terms of providing that information on a desktop and allowing you to download data from national databases to help set up a Basins project with HSPF. So much of that can be available through Basins, or you can use your local data too, and actually use data, local land use coverages and so forth. That many Basins users use HSPF through Basins and use their local data. User training has been available, has dropped off considerably in recent years, but we're actually giving a workshop in Seattle next week. So training is available for the Basin system. There is no comprehensive parameter guidance available at the current time, but there are technical notes to guide you through different aspects of model applications with HSPF. And there is an effort now to upgrade an older document, 1985 document, on water quality parameters and guidance on parameter estimation for water quality constituents, nutrients, toxics, and so forth within the EPA to help not only HSPF but other models in terms of parameter estimation. Its limited spatial definition is not quite as much of a limitation nowadays with the computing power they have on laptops and so forth. So it's really a function of how much detail you put into your model setup and segmentation. It's not a gridded model. It doesn't impose a grid over the watershed, but it allows you to break up in multiple subbasins and design the spatial resolution and temporal resolution to meet the needs of your particular problem. The hydraulics are limited to non-tidal freshwater systems primarily. However, recently we have added some capabilities to include dynamic flow routing comparable to what is in the SWIM model, or a portion of what's in the SWIM model. And I'll mention a little more of that later on. It does do a relatively simplified representation of urban drainage systems, but this can be expanded also with the new capabilities available. It has a limited representation of algal species. Typically, a single phytoplankton and zooplankton species are represented within the stream channel. The benthic algae component has been expanded 3 types of different types of benthic algae in the stream bottoms in the bed. Some recent enhancements and developments that have been funded by others. There's a shallow water table conditions that allows you to track the actual water table as it moves within the soil profile and all the way up to the surface, funded by South Florida Water Management District. the implementation of water quality linkages between land segments for like modeling buffer strips, riparian zones, grass waterways was funded by the Minnesota Pollution Control Agency. Irrigation capabilities are also funded by South Florida Water Management District. The EPA funded the inclusion of simplified snow algorithms. So you have an option to do a very detailed energy balance approach to snow melt and snow accumulation and melt simulation, or you can use a simplified degree day method to allow that in areas where it is not a dominant factor in the watershed processes. There's an online help manual completely available through access through WinHSPF and available as you're running the model. There's a and it's somewhat outdated right now, actually, a program called GenSen that was funded by US EPA and US Geological Survey, and it was designed to basically evaluate alternative scenarios, an interactive program that allow you to make changes to the model, run scenarios, and compare it to a current or baseline condition to evaluate the effects. WinHSPF within basins basically replaces that capability. And there are BMP and report modules were developed, funded by TMDL studies in Georgia, and that allows you to both select BMPs and their efficiencies associated with that in your particular area, and report out the differences of what BMPs do in terms of pollutant loadings. And as I mentioned, the multiple benthal species, benthal algal species, were incorporated, and actually there was a version of 13 and version 12, and it's funded by a Nevada group where that capability was developed. Now I'll give you a flavor of what to expect in the upcoming Basins 4.2 and HSPF 12.4 that are currently undergoing peer review, but will be released probably within the next few months. NLDAS is a national data set of meteorologic constituents, and right now you can download a complete set of meteorologic data to run HSPF at a 1/8 degree cell size. And then there's the NWIS capability. National Water Information System has been upgraded to allow for reading some of the more recent versions of the USGS. Occasionally, the data formats have changed, and this linkage has been broken, but that's been corrected now. And then the NLCD, the National Land Cover Data Set, has been upgraded to include both 2006 and 2011. These are data that you can, when you set up a basins project, it allows you to download all these data coverages automatically to help assist in setting up a basins project with HSPF. The HSPF BMP toolkit has also been incorporated in the basin system to allow you to access capabilities that were put on the web by EPA Athens Group to allow you to develop channel characteristics of BMP tools and LID tools to mitigate the effects of pollution. And so this gives you a kind of direct link to the website, and the capabilities are now included within HSPF. And there's an advanced wetland setup that allows you to choose how to represent wetlands, either as separate retres operations or as per-land operations. And so these capabilities are now within Basins 4.2 and will be forthcoming after peer review. Now within 4.2 will be a version of HSPF referred to as version 12.4. This has a dynamic wave routing capability. It's a subset of the X-strand capabilities within SWIM. It has now a multi-level canopy compartment within per-land. Previously it was just everything above the land surface was considered vegetation with one set of interception and land cover characteristics. In order to represent the effects in forested areas of things like burning underbrush and prescribed burning and other management practices within forested areas, we developed a multi-level canopy, so you can divide that vegetal canopy into 5 different compartments, an overstory, understory, and a litter compartment, for example, represent each of those sequentially in a fashion to better represent what's happening in the above ground compartment. And there are some additional binary output options in version 12.4 for the BMP report module, which is BMP rack. I want to go over briefly the HSPF application process, the steps involved in actually applying HSPF. Well, we've shown it here as a pyramid with the bottom phase being the model setup, phase 1 involving data collection, model input preparation, and parameter evaluation. Second phase being calibration, validation of all the constituents, hydrology, sediment, and water quality. And that's where you go through a process of calibration, adjusting model parameters during the calibration phase, and comparing model results for an extended period, typically 5 to 10 years of calibration. Adjusting the model parameters to get the best fit you can during that period with the observed data, full range of flow values, annual values, monthly values, and then looking at sediment information you have and try to represent sediment concentrations and loadings and water quality. And once you've completed the calibration, then running that model on a different time period and performing a validation step. And this is what we often refer to as model testing, trying to gain confidence that the model is representing what your watershed, and gaining confidence in that representation based on the calibration and validation results. If you can get comparable results during the validation period as you did during the calibration period, then you can have confidence that the model is a good representation of your watershed system. You can then move on to performing model analyses. Excuse me. Modeling scenarios on the watershed, proposing changes in order to improve water retention or water quality conditions on the watershed, simulating that, and then identifying what level of analysis or what level of alternatives you might want to consider in terms of following through with implementation. So this provides information to the decision-making process as to what if things change on the watershed, or how can I change things to make water quality improvements, or to meet water quality standards, or in developing a TMDL and distributing that load allocation to the various contributing sources. And you'll see here that the stakeholder involvement is planned and throughout the process, all the way from model setup to get their inputs on data that's available and what they would like to see, making sure that the modeler understands what the stakeholder understands in terms of how the watershed behaves and what's happening on the watershed, all the way through the decision-making process. The HSPF application process is similar in that regard in terms of first coming up with a study definition, developing a modeling strategy, learning the operational aspects of HSPF, and then going through that pyramid diagram and inputting and managing the time series data. Doing that phase 1 where you prepare the data for use by the model, develop parameter estimations, communicate to the model what the characteristics are of the spatial variability across your watershed, and performing the segmentation process. Going through the calibration validation, and then analyzing various alternative scenarios on the watershed to improve conditions. Study definitions involve defining in detail what the problems and questions for the analysis are and what the study goals are, identifying what data is available and the project resources, both in terms of time, money, and expertise, in order to perform the analysis. The modeling strategy involves identifying the processes, constituents, and sources to be modeled on the watershed. What are the key things that are ongoing on the watershed? What do you need to understand? What particular constituents, whether it's DO that's affecting fish populations, habitat considerations, or if nutrients that maybe affect the algae and water quality conditions that may require a TMDL, and what the sources are, to understand those as you're putting the model together. Performing both the watershed and channel segmentation to make sure that we provide information at the proper spatial resolution and the temporal time step of concern, and that impacts these constituents. And make sure we have the data to support the modeling effort, and then analyzing what the potential human impacts are and how can we change those, or what alternatives can be analyzed to reduce and meet the TMDL or reduce the impacts of the human activities. We recommend that all this, the net result of this, be put together into a simulation plan that provides the results of all these studies, these components of the study, into a plan that you can then use as a communication tool to stakeholders and anyone else interested in the study, and update that as you move along through the actual study itself. And it's a great way of communicating what's being done, and as a key aspect of stakeholder outreach. Constituent sources in HSPF include initial storages for state variables, non-point loadings that the model simulates, point loadings that need to be defined, quantified, and put into the model, any contributions from the atmosphere, especially in terms of nutrients, chemical transformations, releases from the channel bottom, and for air water interface, the transfer across that interface for DO and CO2. Analysis of alternatives requires a complete definition of what the alternative is, whether it's an agricultural management alternative where you may have grassed waterways, conservation tillage, detention basins, or urban alternatives that may involve street sweeping, also detention basins, or treatment alternatives. Define it in much detail as possible so we can develop ways of communicating to the model what the change condition is from a current or a baseline condition. Selecting the constituents that you're simulating that are important to model, and what specific numeric and statistical measures you want to use to evaluate these constituents, whether it's a mean concentration, a concentration duration curve, or a low flow concentration during low flow periods. Whatever that measure is that you're going to use to evaluate the different alternatives. And then representation of alternatives in the model usually involves input changes, the way the model is put together, the consistent configuration, or parameter changes in the model. And these are the three major ways we can make changes on the watershed. And you can't actually make it in the real world, but you can do it within the model and relatively quickly determine what the impact of those changes are likely to be. The amount of time and effort that's involved is really laid out in this slide, more in terms of relative problem definition, modeling strategy, learning operational aspects of HSPF, but then getting into the development of the actual data that runs the model, the parameter development, and the calibration validation. These are the big time sinks really in the model application phase, and they're laid out in a manner sequential, but not entirely some can overlap. The main portion of this, or the main message from this, is that typically this is weeks to months. It's not usually hours or days. It takes a considerable effort in many cases of any kind of significant size watershed of hundreds of square miles. If you're applying it just to a small site, and it can be done to small sites, obviously the time frame will be collapsed. But it has all of these same types of efforts that are involved in that, and smaller size basins also. So I want to just quickly mention, I won't spend too much time on this, but this, I did want to mention that within basins there are a number of things that help these different application steps. As you can see, these are the things I just talked about: study definition, time series, parameter development, calibration, hydrology and water quality, and scenario analysis. There are things, these are the tools that basins provide. These are other inputs and issues that need to be considered as you step through this process. And over on the right, these are the different workshop exercises during the workshops that we provide on basin that allow you to go through these types of model application steps. This will be the core of any kind of webinar on basins, and I'll leave it to that, and hopefully you'll see another webinar on basins coming up sometime in the near future. So, Dino, if you're there, I think we're ready if there are any questions at this point. Dino, are you there?
I'm just doing a time check, and I think we have a lot more content to go. So I'm going to take a couple questions. There are lots of questions coming in, but before I actually take those questions, I want to remind everyone that if your question does not get asked today or answered today, and you still want to contact our speaker, there is going to be a slide with his contact information at the end of the presentation, and you are more than welcome to ask him your question at that time. So I'm just going to ask one or two. Let's see. There was one question about reservoirs and mixed reservoirs, and the capability of HSPF for handling reservoirs. So can HSPF handle shallow reservoirs or those with high residence times, or can it handle all reservoirs?
It's mostly related to relatively shallow reservoirs. There are techniques that are being developed right now, actually, because of the flexibility of HSPF, where you can represent or try to approximate a stratified reservoir by having two quote-unquote stream reaches, one on top of each other, and allowing the interchange by the flexibility within HSPF. But it's primarily related to shallow reservoirs that where the completely mixed assumption is the best appropriate way of representing that. If you do have detailed stratification, it might be best to link HSPF to a separate reservoir model like C=W2 or EFDC, one of the more detailed in-stream models. But there are ways to accommodate some of them if it's not the dominant factor involved in your reservoir.
Okay, great. We're getting a few questions on groundwater and how HSPF handles both groundwater quantity and quality. Maybe you can take a few moments to speak to that.
Mm-hmm. Yeah. It is a very simplified groundwater representation. Each land segment has multiple land uses, and each of those it really drills down all the way to groundwater for each of the land uses. So it has a groundwater storage compartment associated with each of those, and that is soon to contribute back in the storage, and the release from groundwater is like a linear reservoir. There's a recession parameter that controls the rate of outflow from groundwater, and there are actually a couple of parameters that allow you to have nonlinear releases, a nonlinear discharge as a function of the groundwater gradient and calculation of the gradient and the storage and depth within the groundwater box itself. It doesn't give you as much. The only spatial resolution it has within groundwater is what you've imposed from the land surface. So it does have some limitations there. Water quality depends on what options available within HSPF you activate. If you're doing the simplified representation, it allows the user to specify what are the concentrations for your constituent that are being discharged through groundwater. So you can predefine those, or you can put a monthly variation on those concentrations for each of your constituents. So it gives you a fair amount of flexibility in that regard, but it's not simulating the interactions per se. But within the AgChem module, it does do nutrient cycles within the groundwater system, both the shallow and, well, the deep groundwater is either storage or a sink, so it doesn't represent what's happening in deep groundwater, but it has been linked to groundwater models in terms of providing fluxes, for example, to ModFlow that then feed into the ModFlow program and can be linked to look at surface water, groundwater interactions.
Okay, great. I see that we are getting a lot of questions, and they are all very good. However, I think, Tony, you have a lot more content, and I think it would be best to show some of the examples in your later slides. So I'm going to go ahead and just hold off these questions for the final Q&A if we have time, and just ask the participants to please keep those questions coming, and we'll try to answer them as many of those as we can. And thank you for submitting those questions. So Tony, I suggest we just dive back into your presentation.
Okay. I think we're about halfway through overall, and I'll try to speed up a little bit so we have plenty of time at the end for further questions. Now, calibration validation. This is one of a couple of lectures we normally put into our workshops, and I wanted to adapt some for this webinar to give you a sense of what's involved in this step of the model application. I've put up here what's called the American Society for Testing Materials. They proposed definitions. This was a number of years ago. I think it was right around 1980 or 1985 as to what a model is. Assembly of concepts in the form of a mathematical equation that portrays understanding of a natural phenomenon. And basically, for us, for a watershed model, it's assembly of a series of mathematical equations that represent all the processes involved in a watershed system. So it could get very involved mathematically and very complex. But in many cases, it's a very relatively simple representation of individual processes, and the complexity is how do these fit together in the real world and in your real watershed. A verification in terms of this definition is primarily in terms of verifying that the computer code represents the mathematics properly. In calibration and validation, two sides of the coin that where the calibration is a test of the model with known input and output used to adjust or estimating factors for which data are not available. Well, data is usually available for estimating some of the calibration parameters, but their effective values over the land area they represent may be different than the point measurement. So you're refining basically model parameters to best represent the outflows or the results of what's happening on your watershed. And then validation is the opposite of that, or the second step in that, where you take the calibrated model, run it for an additional time period that was not used in calibration, and see how well it performs. And if you have similar performance metrics in the calibration and validation phases, then you can say the model is really a good representation of the particular watershed that it's being applied to. And that's really shown in this kind of modeling process too, where the middle portion here is the model testing phase, calibration, validation. Post-audit, normally that's an after-the-fact test after something has been changed on the watershed. That's not often performed. But you'll also hear this type of statement. I guess I've lost all the animation for some reason on these slides. This was supposed to be animated, but basically all models are wrong, but some are useful. And this was attributed to a mathematician, Box, in 1979. But the utility of the model really depends on the model testing process. And a big part of that, obviously, is the calibration and validation phase. So as you're going through calibration, it's a system. You can view it as basically the model user being a detective, trying to explore all avenues as to why the model and the data don't match up. And sometimes the differences may be dramatic, may be very different. Other times they may be more subtle. But it's a system of going through, looking at inputs, outputs, and potential sources of error or differences, reasons for the differences between the model and the data that you have. So if you look at this diagram, you have the model, a representation, the actual watershed on the right-hand side, and the model representation of that watershed on the left. The analogy in terms of inputs may be if you consider rainfall. A rainfall, the natural system gets the actual rain that falls on the watershed, both in terms of time and intensity as storms move across the area. What we put into the model is what we measure at particular points, and then possibly make some adjustments or a decent analysis to try to get a better sense of what actually fell on the watershed. But it's approximation based on observed values. And every time you make an observation or you take a measurement, there's also always a possibility for an error. So basically what I put in this diagram in these red boxes are the potential sources of errors that could contribute to the differences between your real system, your real watershed, and what the model is predicting. And so you have to be very careful of input errors, because that really is like two strikes against the model. It's really unfair to expect the model to present accurately the output if you don't give it the right inputs. So you have to be very careful on the inputs. The model itself is not perfect. These models are cartoons of reality. So they really try to represent the essence of what's going on, but they can't represent every detail. And sometimes not every detail is important for your particular question that needs to be answered. So there is some possible sources of error within the model. As you go through and estimate parameters between the real world and what you put into the model, you usually have to make some approximations. And that also introduces a source of error in terms of estimating what the parameter values are for your model. You then go through the calibration validation process here, where you get model outputs, you compare to your observed outputs, and there's some sources of error here. Although you'll get a nice hydrograph for a storm event or for a daily flow, it's usually should be considered really a fuzzy bounds about the actual values. There's some uncertainty, due to measurement errors, analytical errors, or differences. So you're actually comparing it point to point and for a particular value, but there's a range of uncertainty about those values, so it's important to consider that. And the other source within the calibration is a calibration parameter adjustment. You're adjusting parameters, comparing model outputs to observed values. There are errors on both ends, and depending on how much time and money you have to calibrate or expertise to calibrate, you may not get the best optimized set of parameters, and oftentimes it's not possible to get an optimized set. So there's sources of error here also. But the point is that as you're doing this, it's important to include consideration of what the magnitudes of these differences and errors might be as you go through the calibration and validation. And then ultimately, model testing represents the net outcome of this. So, but if you go through this process, you resolve that the errors are within acceptable bounds, and you get a pretty good match of observed and simulated data, simulated values, then you get to the point where you have an acceptance or a confidence in the model, and you start to be able to believe that it is a good representation of your watershed. If you get to that point, then if you really believe it and you have confidence in the model, it has a very powerful tool. It's like having a monitoring station at every point in the watershed where you need information for whatever your water resources, water quality planning and management decision is. And that can be a very powerful tool, and many of our clients do use it in that fashion, where they don't have monitoring data. If a model has been set up for the watershed and a discharger or a developer wants information, they'll provide values from the model because it's the best available. But anyway, it's a very powerful tool if you get to this step in the process. The types of comparisons we make on modeling include point-to-point paired data performance. So you have a simulated point for a certain hour, you have a recorded data value, and you compare those point-to-point. That's the toughest performance that you can require. We usually do those to show if there's a time difference or time lag or time step difference or value differences. But many times the time step differences may not be too critical. We also look at time and space integrated paired data. So you might look at daily values and the total daily flows, or mean daily concentrations and concentrations collected averaged over that day for the values and samples that are taken. So this is time and space integrated, and a little easier comparison to see if you're in the right ballpark or you're getting a good agreement. Or you can also look at the frequency domain. What percent of time, like a flow duration or a concentration duration frequency, you can generate that from the model, and depends if you have enough data, especially concentration data where you may not have as many samples, you may need to break it down to paired data samples there and look at the observed data on the day and the actual simulated values for that day, and pair those up for only the days where you have data and do that kind of comparison. So there's a variety of different ways of comparing model results with observed samples, observed observations. There are a number of calibration issues that have led to the approach that we've taken over the years for calibration and validation. And things have changed. We use more statistical tests now than we used to a number of years ago. But it's important to realize that the models are approximations of reality. So they can't precisely represent everything in your watershed, in your natural system. It's generally accepted that there's no accepted statistic or test that everyone agrees determines whether a model is good or not, or is valid or not. So you have to use both graphical comparisons and statistical tests. And most standards, modeling standards or agency standards for modeling, include or require looking at or reviewing both of these, the graphical comparisons and statistical tests. And I'll show you some of that in model results that I'll present a little later on. But you also need to recognize that the models can't be expected to be more accurate than any errors or confidence intervals that you have, excuse me, have with the input data or the observed data. And so it's important to consider what these confidence intervals are as you're to kind of moderate the demands on the model in terms of accuracy. So what we're saying basically is that a weight of evidence approach is becoming the preferred practice for model calibration and validation. That there are a variety of graphical and statistical test comparisons you need to make, and then looking at the total picture of all of these, it provides you the kind of overall weight of evidence as to whether the model is a good representation of your watershed. This involves, for hydrology, looking at annual and monthly runoff volumes, the mean runoff during the simulation period, the daily time series observed in simulated daily flows, scatter plot, the flow frequency curves. Typically it's done for daily values, and for storm hydrographs, hourly or less. You need to look at the water balance components. If you models are set up for individual land uses within your watershed, you need to look at this type of display for each land use and for the watershed as a whole. What's coming in as a supply in terms of precipitation and any irrigation that may be additional water from outside the watershed system. A total runoff and the distribution into its components, overland flow, inner flow, and base flow. This comes into the calibration because the observation that we have for flow is just the total flow. We don't know if it can, at what time, what fraction comes from overland flow, inner flow, and base flow, but we can impose variations and know that during major storm events, much of it will be coming from from overland flow. After the peak, much of it comes from inner flow, and then subsequently from base flow. So all of these components are available. Only the model prints out, what the distributions are and what those flow components. And then to complete the water balance, we need to know where the evapotranspiration is coming from that makes up for losses. And these are the various soil zones of where ET is derived from. And then there may be some deep groundwater recharge or losses from the system that need to be taken into account in order to close the water balance and complete the water balance analysis. Graphical and statistical tests are shown here. I won't go through all of these, but these are the types of things to look at, and I'll show examples of most all of these in subsequent slides. But some of the statistical tests include mean error, mean absolute error, bias statistic, correlation coefficients, and coefficient of model fit efficiency. This is also called the Nash Sutcliffe coefficient that has been widely used in recent years. And there are efforts actually ongoing now by various groups to say what are the ranges of these coefficients or these metrics that correspond to acceptable calibration or a good, fair, or poor calibration or validation. And some of those efforts are ongoing at the current time. Here's some general guidance. Users always ask us, well, how do we know we have a good calibration or a poor one? So we put together this slide many years ago. I guess it's going on 16 years or so since it was first published as part of basins workshops we were giving. But these are differences in monthly and annual values. We'd expect storm differences may be somewhat higher. It also depends on the quality and detail of the input and calibration data, why you're doing the model, what other assessment procedures you have, and how much time and money you have to do it. But basically for flow, you can see the values are here in terms of percent differences between simulated and recorded values, from less than 10 for very good to 15 to 25 for a fair calibration for hydrology. Sediment is one of the more difficult constituents. We would consider 30 to 45% to be fair for sediment, whereas much lower for hydrology and flow, and even lower for water temperature. We can often do relatively good in terms of matching diurnal variations and seasonal variations in water temperature. Nutrients, water quality, and pesticides are somewhere in between that. But these are kind of the ranges we recommend in terms of guiding you in terms of what might be fair, good, or very good calibration or model results. We've also provided this kind of diagram to guide you in terms of correlation coefficient or R-squared value coefficient of determination. And the way you read this is that if you calculate the R and R-squared values based on daily flows, this
All right, while we wait for Tony to get his screen back together, I would like to acknowledge the Water Quality Modeling Steering Committee, which you see right here. A bunch of savvy modelers that came together to try to share modeling knowledge for the broader community. So thank you to everyone. As I mentioned earlier in the webinar, should you have any additional questions for Tony, or if your question wasn't answered today, feel free to contact him. His contact information is shown on the screen with his email address, and he would be very happy to get in touch with you at that time. You can download a certificate of attendance at the link shown on the current slide. Copy and paste this link into your browser to download the PDF document, which you can then personalize with the names of everyone watching from your location. More importantly, you can find future webinar registration links and a recording of today's presentation on EPA's Water Quality Modeling Workgroup webpage. And the link to that page is also shown at the bottom of this slide. We will have more webinars. The next one is titled Sediment Modeling, and that will be held in some date in November of 2016. And that will be followed by EFDC in December. EFDC stands for Environmental Fluid Dynamics Code, and it's a sediment transport type model. LSPC is a variation of HSPF. It's a different type of watershed model, and that will be held in January. And then we will have WASP in late winter. Details will be available on our Water Quality Modeling Workgroup webpage shown here. And let's see how Tony's doing. I think he's about ready to transfer back onto the presentation. Tony, are you there?
This was the slide I was on. Did I finish this before we had problems?
I think you went through it sufficiently.
Okay. Okay, I'll go through this. I'll talk about sediment calibration. There are two main phases in sediment calibration. Is to estimate target setting rate, loading rates by land use, then calibrate the modeling, what the model produces in terms of loading rates to match up to the loading rates you have by land use. And then once you have the loading rates by land use within reasonable ranges, then you go through an in-stream calibration that involves estimating parameters, making a separate assessment as to how much of the sediment is actually contributed from surface sources versus channel contributions, determining and to see if you had actual channel scour or deposition out in your watershed, and if you're degrading streams or are grading streams in depositing streams in various portions of your watershed, and make the model match that up. There are model parameters for shear stress and critical values of shear stress for scour and deposition that are adjusted to allow you to impose that type of variation throughout your watershed. Water quality calibration involves estimating all the parameters associated with land use specific accumulation and removal rates, wash-off rates, and subsurface concentrations, calculating these loading rates compared to your non-point loading rates, calibrating in-stream water temperature, comparing observed and simulated concentrations, and then analyzing the results and seeing if iteration is needed, or if you are matching close enough. The two examples I wanted to present, and I'll go through some of this relatively quickly. An example on the Connecticut River watershed in New England and Housatonic River in western Massachusetts. This is the state of Connecticut in the red line outline and the watersheds. We were asked by the Connecticut DEP, Department of Environmental Protection, to provide nutrient loadings to Long Island Sound, which is basically the body of water just off the coast here in New England. The watershed, we identified 3 test watersheds, the ones in green that represented urban, agricultural, rural, and then a mixed watershed. And those, we first applied the model to each of those, and then extended those parameters to major river basins. One on the Quinnebog was way over here in the east, the Farmington here in the middle of the state, and then the Housatonic that was started up in Massachusetts and comes down through Connecticut. So we took these calibrations for each of these 3, extended the parameters to the large river basins, and then extended those parameters throughout the state to calculate nutrient loadings to Long Island Sound. And the purpose of this was to provide loadings to their model of Long Island Sound because of anoxic conditions in the sound and the need to reduce especially nitrogen coming off the land. Our hydrology calibration for the CT Connecticut watershed model went through a number of steps. So we had a calibration period from 91 to 95, a validation period for an earlier time period, 86 to 90. And that was so we could, we had more data during the 91-95 period, more water quality data. So we definitely wanted our best calibration during that period so that we could then have a good chance for a water quality simulation. These are the 3 test watersheds we calibrated to, and these are the 3 major river basins. You can see the mean observed flow. I'll be showing results for the Farmington River. So look at these. Basically, we got over the 5-year period, we had a mean observed flow of 26.2 simulated 26. So very small difference in our value of 0.85 and for daily and 0.92 for monthly. So these are in the range of very good calibrations. We get similar results for the validation period, where we ended up with our value of 0.87, actually better than the calibration period, and 0.94. So in this case, we had statistics produced that were actually better. So the model was a good representation of that area. But you can see the tabulations. All of these values are in quite good ranges for these particular values. This was done a number of years ago, and the correlation was the primary statistic, the metric that we used at that time. This is a daily flow sequence of at the Farmington gauge. During the calibration period, you can see we had a number of storms we would over-simulate, others we would under-simulate, but overall, up and down, you can see it's a pretty good, it matches the flows pretty well as it tracks throughout the different years. And then at the top, you can see it's responding to these rainfall amounts. So the highest peak, or just about the highest peak, was a result of some of these extreme rainfall events. This was during the validation period, and we actually, you can see that we, again, similar type response. We did really well on some of these peak events, and then the metric of the correlation coefficient confirms that you see here that we do a good job of the flow simulation. This is the flow duration curve, range from 100 to 10,000 here on the vertical scale, and again, this is a percent chance exceedance with a probability scale that highlights or emphasizes the extremes and you can see that we match well throughout it. There is some variation down at the bottom here, but that's to be expected because we didn't have a database of diversions, and there's a series of small diversions throughout the state that we could not represent without data. You see some variation, and this really shows up in the validation. We do well throughout most of the flows, but we do some range at the very low flows because of the diversion issue. The scatter plots reflect the same type of simulation. This is a daily scatter plot with a correlation of 0.85 at the same site, Farmington. This is the monthly, and you can see it's 0.92. Some slight bias here in terms of the extreme values, but overall very good. Looking at the loading rates, the target and the simulated, this researcher, Frank, was in Connecticut, was well regarded, and his estimates of loading rates have been used throughout the state for many years in terms of estimating what's coming from urban versus agriculture versus forest. For total nitrogen and total phosphorus, the values here were generally accepted. Something unusual in my experience was that this was the first time you would see urban loadings typically higher, maybe by a factor of 2 from agriculture. And the issue here is that agriculture is not the type of Midwest highly intensive farming agriculture. It's more hobby farms and small orchards and things like that. So it's logical as to why this would happen, but we basically made the model kind of match up to these ranges within some latitude. And so the model produces urban loading rates from pervious and impervious areas, then agriculture and a range in forest and wetlands. And these basically match up quite well with the available data, or more of a consistency check to make sure we're really representing the non-point sources in a reasonable fashion. The tool we used at that time was Jensen, and it allows you to do these multiple water quality plots because water quality really has to be calibrated jointly. You can't just calibrate nitrate irrespective of ammonia and DO and so forth, because all the constituents are interrelated, and changing one will have impacts on the other. So they need to be calibrated in a unified approach. Here's the results for the observed and simulated daily concentrations at Tariffville. This is on the Farmington River, and you can see we track the concentrations really well. We do reasonably good on some of the low concentrations, but you can see we're not getting down into very low values here. It's not approaching values of 5 or not, so it's really doing pretty well, and relatively high values of DO throughout. This is ammonia simulation, and you can see we do track. We don't hit all the extreme points, but we do quite well throughout the simulation. This is the kind of variation you're likely to see with water quality calibration. You're likely to have a few outliers that you have no real explanation for, the model can't really represent, but it seems to track the bulk of the data in a pretty good fashion. This is the total nitrogen. That includes nitrate, ammonia, and organic nitrogen. I think we had Kelvin nitrogen values to fill in the organic component. And you see we had an extreme one up here of 3 that we never even got close to. And phosphorus, we tended to be high on phosphorus. The primary reason was that there was very little sediment data. And phosphorus is such a highly sorbed that it really depends on how well you're doing your sediment simulation, but there was very little sediment data for calibration. And that's probably why we tended to overestimate the phosphorus concentration, because there was no settling in stream, so the in-stream sediment phosphorus interactions were not adequately represented. is total organic carbon, which was another constituent we did in terms of loading the Long Island Sound model. And so all these different sites, basically 3 main stem sites, 3 test sites, we looked at each of the constituents, calculated their observed values, averages of the data, the simulated values on the days we had data, and then looked at their ratios of the observed to simulated, and tabulated that here. I know you can't read all those, but we put a summary here in terms of the average values of those ratios and the range of those ratios for each of the constituents we modeled: DO, the nitrogen components, the phosphate components, and organic carbon. And you can see we do reasonably well for oxygen. Nitrogen is also in a relatively good range, the average values in the 0.9 range, and bracketing a value of 1 in terms of this ratio of observed to simulated. You can see we over-simulated the phosphorus components, 1.3 to 1.4, and usually greater than 1 here, again, because of the lack of sediment. For the Housatonic River, and I'll just wrap this up really quickly here, we had 2 gauges, an upper watershed of about 50 square miles, a watershed outlet of about 300 square miles. So we calibrated at both sites, mostly a rural watershed, 70% forest, 13% ag, but it was mostly small rural towns, 11% agriculture, and 6% wetlands. We looked at a simulation period of about 10 years here, 1990 to 1999. Tabulated annual values, observed values, and percent errors. And you can see we did real well on the overall simulation period, only a 1.4% error difference in the observed versus simulated flows. And we did pretty good in the year-to-year variations. We had about a 15% difference, positive and minus, in terms of variations year to year, which is unusual. Many times you'll see a higher differences than that. And here are some other statistics in terms of the upstream tributary and watershed outlet runoff, average runoff in inches. You can see the comparison. These are the errors. So those are criteria of about 10. For the upper watershed, we were within 3.4%, and criteria of 10 also for the lower watershed, and we were 1.4. Then we looked at the high flow differences and the low flow differences, and then this last one is the percent difference in average storm peak. We had about a 10% difference at the upper watershed, and only a 1% at the lower watershed. And this is an average of 31 storms occurring for the simulation period between 1990 and 99, and it calculated the volume and the actual peak flow, peak daily flow for each of those events. Other ways of looking at it, we also looked at not only the correlation coefficient, but the R-squared values, the mean error in CFS, mean squared error, and this is that model fit efficiency, which we started assessing in the recent past, in the last 10 years. This is also called the Nash-Sutcliffe coefficient, for those of you who are knowledgeable in terms of metrics. The daily value of 0.73 and monthly of 0.87 are both very good levels of correlation. To look at seasonal variations, we looked at how well we were simulating the average monthly values, and you can see there is a considerable range, but generally less than 20%, pretty consistently less than 20%. Sometimes lower in the winter months and or fall months, a little higher in the winter, and because snow melt was such a key aspect of this watershed, and that's usually a little more difficult to simulate. Some differences in the spring, but generally pretty good simulation in terms of differences there. We also looked in terms of the water balance. This is the expected range, and this is what we simulated. The expected range is data from not related to modeling at all. This was based on a USGS watershed report that presented ranges expected for the water balance in terms of the range of precipitation for the watershed range from 43 to 53 inches. Runoff at the two gauges were in the 23 to 27. ET was 20 to 23, and the recharge was estimated in the range of 1 to 4 inches. And we did well in terms of representing that aspect of it. We also looked at it by land use so that we had confidence we were representing the land uses differently in a good way. And this is our summary of the weight of evidence approach in terms of the various metrics and the overall calibration performance, good to very good, for basically all the things that we had looked at in terms of the errors over the entire period, the annual volumes, ranges, monthly ranges, R-squared values, daily and monthly, flow duration, water balance, and storm event statistics. So anyway, I wanted to leave a couple of closing messages with you that the watershed models like HSPF can be valuable tools for TMDL development. But they do have to be applied and used appropriately. So some guidance and training in the use of the tools is really highly recommended. And make an assessment as to whether you have adequate data to do a calibration, a reasonable calibration of the model. And you do need to recognize that the models have limitations. There are things that some models cannot adequately represent that may be important in your particular situation. And finally, I'd like to close with this statement I got many years ago that with poor assumptions, a user can make more mistakes with a computer in a millisecond than he could in a lifetime of common sense. So it's important to look at the model results and the comparisons with a sense of what is reasonable, are these numbers appropriate, and does it pass a test of common sense that they make sense. When I first got this quote, this was like a computer in a minute, but that's a lifetime in terms of current computers. And I upgraded it from a man can make more mistakes to a user to be more gender neutral. So, and with that, I think this is my last slide. Thank you for listening.
Excellent job, Tony, and thank you for being patient with the technical issues we were having. I think you really rolled with the punches there, and I appreciate that. You did make up some time, and I think that's really good. We have lots of questions that have come in. I'm going to leave the screen up on the contact information slide in case people do want to reach out to you later. But before we get into some of the questions, I think we have a fourth poll that we'd like to ask our participants if they could answer. And you should see that on your screen now, and it just has a couple different options for trainings. And if you could submit your response, that would be great. Looks like a lot of people want a lot of HSPF training, so there's about 80%. Now it's dropping a little bit, but the majority of people would like 4 to 5 days of basin or HSPF specific training. So that's very interesting. Thank you for participating in the poll. We have a bunch of really good questions that I'd like to ask you, Tony, while we have the available time. Many of them deal with the capability of HSPF to handle different situations. So I'll try to bunch them up together. There's some questions about model application in transition zones from stream reaches to reservoirs. Some people are asking about if HSPF can be used to model wetlands. Yeah, I'll leave it like that.
Okay. Yeah, transition zones, I guess, are more an issue of how well you discretize your stream channel in those areas and the associated contributing area. Yeah, you can. There's no limitation really in terms of the size of stream segments you have. You probably need smaller in terms of temporal resolution, more detailed simulations. You might need to run the stream channel in 5 or 15-minute increment mode, depending on the size of your watershed. It's important to see what's happening in that transition zone. It's not going to give you backwater type things where if you're thinking the lake of the level of the reservoir should back up into the stream channel. It doesn't represent that phenomenon. You would need a more detailed hydrodynamic model to really handle that. But it does pretty well at the at the overall scale, at the hourly 15-minute time step, and does track overall feeding reservoirs. It hasn't been an issue really in most of our applications. In terms of wetlands, we would typically represent that as a separate model segment, a model land use that has its own parameters, and you could, we can even, it has a capability to track water tables so that you can actually calibrate to the depth of water in the wetlands if you have data. But it is mostly data-driven, and in fact, we don't usually see that level of kind of data in the specific to wetlands in most of our applications. But we also have a capability to have one land area tributary to another land area, in which case, the drainage contributing to the wetland could be represented separately as inputs to a wetland, either a reach segment or a land segment. And there is a new capability in there to assist in terms of representing wetlands as a stream reach, so you can directly track water levels a little easier than as if it was a land segment. And that'll be coming out in the more recent recent upcoming release.
Excellent. Thanks, Tony. We do have a question asking if you could provide an example of how parameter inputs are changed to analyze different alternatives. Parameter inputs. Well, we sometimes do that with conservation tillage, where it's defined by the Soil Conservation Service as at least 30% of the residue, crop residue, remains in after harvest and is available through the winter to the following spring. So your land cover values, for example, compared to conventional tillage where they may plow in the residue and your cover essentially goes to 0 in the fall. With the conservation tillage, the residue remains, the cover factor for preventing erosion stays high, your surface storage and surface detention, your surface roughness would stay high compared to the conventional tillage. And that's where you would actually have different parameters to represent the different agricultural practices. And that's more in the terms of land parameters. For BMPs or detention basins, you could change the different removal efficiencies depending on what kind of detention basin you have, or you're setting it up so that it has higher removal or screens or things like that would remove a higher fraction of solids and objects, and that may contribute to sediment. So you could change removal factors there. Many times it's more how the system is configured
So you might replace a stream reach with a detention basin and see what impact that has downstream compared to not having the detention basin in that particular portion of the watershed.
Great. Thanks, Tony. There are a few questions dealing with the model handling scarcity of data and how you would approach that, as well as how much data is needed in terms of time series inputs for the model. If you only have a few years, how do you make that work?
Yeah, well, you have to kind of deal with what you have. We have done calibrations on just a few years of data. It depends if it's the few years cover a wide enough range of conditions. You wouldn't want to calibrate to 2 average years and then go run it on a 10-year period that has extreme rainfall or extreme drought. So it's pushing it beyond what the parameters could handle. And especially for water quality, we often have, grab samples. We may have 6 or 8 samples throughout the year, oftentimes in low flow conditions, and yet the model simulates all flow conditions. And if surface runoff is a big contributor, you'd see that you'd be getting big pulses of contaminants coming through during storm events that may not be represented by your water quality data. So that's kind of a normal behavior that you might expect from the model, and that it'd be difficult to kind of match it up with the low flow concentrations that are probably during periods when their only base flow is really contributing to the stream channel. So it's
okay.
Yeah, without data, it's really hard to do modeling unless you have another basis for thinking that the model provides a good representation. It will calibrate it to a neighboring basin, for example. Or we would also look for a neighboring site or another, the closest USGS site that would give you a longer time period. Even if it's a much bigger watershed, it would allow you to say, well, it works down here. There's a good chance it'll, the parameters will give us a reasonable approximation for the smaller site that may only have a few years of data.
Okay, great. There are a few questions that are focusing on extracting the data out of the model, specifically, pulling flows from, a middle point or a middle segment of a watershed, and, getting those flows that come from the hydrographs. Can you speak to the model's capability to extract that sort of information?
Yeah, you can. You really set up the model segmentation or the reach segmentation so that you can output flow values, concentrations, loads, etc., at the endpoint, at the outlet of each reach. So if there is a point where you need information, you would set up your model so you have a reach endpoint there. We have software now that we've been working on for a few years and adding capabilities that make that easier to extract information from the model. It's an interactive program. It's an offshoot of the expert system that was developed for HSPF a number of years ago, and we call it EXP Plus or HSP EXP Plus. That's available to basically help post-process model results, because so many of these are written to either DBF files or the database files, WDM files, and you need programs to extract it from there, and we're pulling that together, or actually have pulled it together into a program to help extract that. Otherwise, you'd have to simply, you can actually just have the model output a data file from the WDM file, but you'd be running the model to do that.
Okay.
If someone wants to be on the if they want to sign up for the Basin's listserv, these kinds of questions are answered, by many users and stuff that I receive those messages on the listserv. So that's one way of getting additional information without having to pay someone.
Great. Thanks, Tony. So we have about 5 minutes left, and we have a lot of questions, and I'll just try to pick as many as I can. But I just wanted to remind you that Tony's contact information is on the slide showing, and the Basin's listserv is another good resource that you could tap into. The next question comes asking if there's any guidelines or recommendations for choosing when to turn on the nitrate or phosphorus modules as opposed to P-qual.
In any first application, it's probably best to use the P-qual, the simplified approach, unless your watershed is dominated with agriculture and you have enough information in terms of fertilizer application rates and crop yields and things like that that all go into doing a nutrient balance on the agricultural areas. Even if you're going to go that route, ultimately it might be worth doing a first approximation using the P-qual routines, just to get a sense of what range of loadings might be appropriate for what you're seeing in your in-stream concentrations.
Okay, great. We have a question from earlier on that I thought was pretty good. If there's no specific parameter guidance available, what do you suggest starting with to help with model calibration?
There's no comprehensive calibration guidance available. There are a number of documents on the Basin's website. There's a tech note number 6, which is the parameter guidance for hydrology, to get people started on the hydrology, and that's usually the first thing you have to do. And that lays out all the hydrology parameters and the hydraulics parameters and snow parameters. It has a discussion on each of them and has typical and possible ranges for each of the parameters. So you can get started on the hydrology. There isn't anything for sediment or water quality, but when you get to water quality calibration, there is a document by Tetra Tech in 1985 that's currently being updated. I think they're only about halfway through that project right now, but it's a guidance manual for in-stream parameters for many models, not just HSPF, but for a number of water quality models.
Excellent. Thanks, Tony. I see we only have 2 minutes left, and I don't think that we'll be able to do the rest of these questions any justice in that amount of time. So I would just like to say we will try to answer them later directly from Tony or some other avenue. And I appreciate you submitting those questions. I have up on the slide the participation certificate and the URL link to the Water Quality Modeling Workgroup webpage, where you can access all of the archived webinars, and in a couple weeks you'll be able to access the archive for this webinar as well. At this time, I'd like to conclude today's webinar and thank our amazing speaker, Tony Donigian. And of course, thanks to everyone who joined us, and looking forward to having you participate in our future installments of this webinar series. That ends our webinar for today. Thank you again for joining us.